In this lab we will study the rheology of polymers. Rheology is the study of the flow of materials, and so we'll look at some parameters of rheology and specifically viscosity of polymers. We'll look at polyvinyl alcohol in particular, and then what this 2-week experiment what you'll do each week. So rheology, as I said, is the study of flow of materials, and a common rheological measurement is viscosity, which is defined as shear versus strain, or our formula here. This is the symbol for viscosity. This is the symbol for shear stress, and this gamma with the dot is the symbol for strain or shear rate. So the shear stress, or the force, divided by the rate is the viscosity. So this is going to give you a linear relationship, which is considered a Newtonian fluid. A non-Newtonian fluid is nonlinear and will follow a power law. And so you have two situations depending on the power here. You either have shear thinning, which is also known as a pseudoplastic, or shear thickening, which is known as a dilatant. So let's plot this out instead of having just formulas. Let's look at the graphs. So shear stress divided by shear rate, if it's a constant, that is a straight line here, which would be a Newtonian fluid. If, on the other hand, the curve increases, that's a shear thickening or a dilatant material, such as quicksand. If you force quicksand, the more force you apply, the faster you apply force, the thicker it gets, the more viscous it gets, and that's how you get stuck in quicksand. On the other hand, you could have a material that is shear thinning or pseudoplastic, that the faster you pull it, the less the viscosity increases, let's put it that way. An actual plastic has could be Newtonian, but starts with a non-zero shear stress. So it's a solid at the particular temperature you're working at, and when you initially apply stress, nothing happens. It's still a solid. You have to apply more stress in order to cause it to deform. So a good example of this would be, say, a stick of butter. So plastic means that the solid that can be deformed. Often we conflate plastic with polymer. Many polymers have plastic properties, but plasticity is a particular rheological property of a material. So these are the time-independent viscosity. There can also be time-dependent viscosity. So here we've plotted a shear stress versus shear rate curve, and as we apply the shear, the faster the rate, the less the stress, so the viscosity is decreasing. But then we returned back to our starting point, and the curve did not superimpose directly on the original line. It's a little bit less. So the viscosity is lower after we went through this process. So the time we worked the material, or the material has a kind of memory of what happened to it. And this particular case, when it's more fluid, that's called a thixotropic material, and we encounter this a lot, right? The more you work a say silly putty, the more you work it, the looser it becomes. The opposite would be anti-thixotropic. An example of that would be bread dough. The more you work it, the thicker it becomes, or the harder it becomes to move, the more viscous it becomes over time. Okay, so you're going to work with a household material and make graphs like this in order to characterize, is it a plastic, is it Newtonian, is it non-Newtonian, that sort of thing. In part 2, you're going to look specifically at polymers. We said these viscous materials may or may not be polymers. We're going to look at polymer solution, and we're going to look at the viscosity because we want to know the molecular weight of a polymer. Now, many polymers are made in such a way that they are polydisperse. So here we have molecular weight, and there's a range of molecular weights, and the number of molecules that have a particular weight, we could have a distribution like this. This is a polydisperse molecular weight, and that's because the reaction, well, we know molecules in a solution have a distribution of energies, actually very, very similar to this from our kinetic molecular theory. And in the reaction of a polymer, you need to react monomer molecules together in a growing chain to make the polymer. And some molecules won't have much energy, and so they'll stop reacting. The chain won't be very long, it'll have a low molecular weight. Other molecules will have enough energy to keep reacting and make a longer and longer chain with more molecular weight. So how do we talk about what is the molecular weight of this polymer? Well, it's a range, and so we need to talk about some kind of averages. So here's an average. This is the number average, the m sub n, number average molecular weight. M sub v would be the viscosity average molecular weight. M sub w would be the weighted average molecular weight, and m sub z is the z average. So, for example, the number average molecular weight you can get by this equation, where this p partition function is the molar mass distribution function. So in other words, the shape of this curve here is here, and then that's the molecular weight, and so you're going to sum from 0 to infinity the area under the curve. Depending on the curve shape, then you would get a particular number average. Viscosity average is what we're going to measure in this experiment, and the viscosity average is similar to the number average, but there's this exponential factor here, A, which we'll learn later has to do with polymer coiling, because we're looking at when we look at the viscosity average, we're actually looking at a solution of the polymer. So what is the viscosity of a polymer? Well, the relative viscosity is our initial measurement, which we get by measuring the viscosity of the solvent and then the viscosity of the solution. This would be a dilute solution of the polymer in the solvent. It's going to be more viscous than the solvent, and the ratio of that more viscosity is our relative viscosity. Specific viscosity is relative viscosity minus 1, and then intrinsic viscosity, which is really what we want to know, because that takes into account concentration. So a more concentrated solution would expect to have a higher viscosity. So the relative viscosity depends on concentration. Intrinsic viscosity does not depend on concentration. We take the specific viscosity, divide it by the concentration, and go to the limit where the concentration is 0. Clearly you can't actually measure that because that would be 0, right? Or infinity. Anyway, what you're going to do is plot concentration versus specific viscosity, and you'll have some data points. Connect the line, and that y-intercept there, that is the specific viscosity, because that would be where the concentration goes to 0. Okay, so we want to find this because of the most important relationship in polymer science, the Mark-Houwenk relationship, which tells us that the intrinsic viscosity of a polymer is related to the viscosity average molar mass of that polymer. It's related by a constant here and then an exponential factor. This is that same exponential factor I mentioned before. So where do these come from? They're experimentally determined. They depend on the particular solvent, polymer combination, and the temperature at which the experiment's measured. So for our sample, we're going to look at polyvinyl alcohol, and in water, so that's our solvent, our polymer, our temperature. Those three things are known, they've been measured, and that's the value for K, and this is the value for A. So if we can measure the intrinsic viscosity, we can then calculate the viscosity average molar mass of the polymer. Where does this relationship come from? It comes from this model that actually is based on a relationship that Einstein developed for the viscosity of a mixture of a fluid with hard spheres. We don't have hard spheres, we have a polymer, and but the polymer coils up, and depending on the size of the polymer, you'll have a equivalent sphere, or a volume of space that the coiled polymer occupies, which has an equivalent radius here. So the radius of this volume of space that the polymer occupies, which is equivalent to a sphere. And the reason the polymer coils up to occupy this space is because it does not want to interact with its solvent. So this is called a non-solvent, or a bad solvent for the polymer, also called a fluorine theta solvent. So the polymer will coil up so that the solvent doesn't interact with it, and when it's all coiled up like that, then it'll rotate kind of like a sphere in this fluid. And in our experiment, we're going to rotate a spindle in the fluid, which will set up flow depending on our rotation rate. Then we will cause the fluid to move. The layer of fluid closest to the spindle will move faster than the next layer, and so on. And this layer of flowing solvent, that's called laminar flow, and it's in these layers. And then the polymer will respond to that and tumble like a sphere. So that's where the Mark-Houwenk relationship comes from, and the A factor here tells us how well this polymer coils up in this solvent. If it was perfectly coiled up as a hard sphere, A would be 0.5. So you can see our particular example, polyvinyl alcohol in water, is not completely coiled up. And so why do we want to measure the molar mass of the polymer? Well, it's very important for the properties of the polymer. But in our particular case, we want to look at how the polymer formed. So polyvinyl alcohol has this general formula where there's n number of vinyl alcohol molecules linked together in a chain. This would be a normal orientation. But every now and then, the OH side of the vinyl alcohol will attach to another OH side, making a head-to-head linkage. And that's going to have slightly different properties than this polymer chain. So we want to know what's the frequency of the head-to-head occurrences. And we're going to use periodate to cleave that glycol linkage there. So then we'll measure the ratio, delta, the ratio of the polymer weights, weighted averages, the undegraded polymer and then the polymer that got cleaved at these head-to-head linkages, which would be a smaller polymer. But there would be more of them, right? You'd have, for each one of these, you'd make two polymers. Okay, so that's what this is. This number average of the degraded polymer, the normal average over the monomer mass here. So the monomer mass is 44 grams. This is the monomer here. You can check that. And so that's number average, but then actually because of this, because we know A, we know the relationship between M sub n and M sub v, which is this here. So we can plug that in to convert from number average molar mass to viscosity average molar mass, which is what you'll actually be measuring. So we can find delta, the ratio of, or the fraction of the head-to-head to normal linkages in the polymer sample. So just to remind you, we're going to find the intrinsic viscosity by doing this plot here. We can actually, we'll do both. Specific viscosity curve, but then also the relative viscosity curve should end up at the same point on the y-axis, concentration 0. And you'll do this measurement or series of measurements, calculate or extrapolate to find the intrinsic viscosity for both the normal and the degraded or cleaved polyvinyl alcohol. So week 1, you're going to learn about how to use the viscometer. You're going to learn about rheology by looking at a common household product, and watch the video for how to use the viscometer. You'll look at 10 speeds, both increasing 1 minute each and then decreasing. So you'll see, is there a time dependence to the rheological properties of the material. While you're doing that measurement, I suggest you prepare your polymer solution that you'll use in the following week. Make at least 2 dilutions, react with periodate, so you should have 3 solutions of polymer and 3 solutions of degraded or periodate reacted polymer. And then we're going to use the ultra low viscosity adapter for the viscometer. Again, watch the video how to do that. And we want to do that at constant temperature because we know what K and A are in the Mark-Houghton relationship for 25 degrees. So once you collect all that viscosity data which will be the speed of the spindle and the viscosity value in centipoise. Then you'll need to do some conversions, find shear stress, plot viscosity and shear stress, so that you can then classify the rheological behavior of the fluid. Remember, I showed you shear stress versus shear rate, which is the definition of viscosity. The shape of that curve is what you use to classify the rheologic behavior. And then if it's a curve, you need the power law. If it's a straight line, you can just use a linear regression and the Newtonian relationship. For the intrinsic viscosity of polymer, you'll find the viscosities of the solutions and the solvents, so then you can calculate relative viscosity. From that you can calculate specific viscosity. From that you can plot versus concentration. From that you can extrapolate to find intrinsic viscosity. You should have two values, one for the original and one for the degraded polymer. Then you can, from the intrinsic viscosity, calculate the viscosity average molar mass, and then from that ratio find delta.